I'll give you a 5-minute window. There we go. Okay. Try and stand right. So you're on.
Should I use both? Or?
You can use them. Should be.
Hi everyone, it's great to be here. So I'm Kristo Ment. I am currently a final year graduate student at Harvard, and I've been working with Dave Charbonneau. And I'm here today to share some interesting results from my study of low mass dwarfs using TESS data. And to motivate, the questions or the results of the study, I would like to start by summarizing what we knew about the planet demographics around low mass stars before TESS. So this is mostly based on data from the Kepler mission. We know that dwarfs have the greatest or have more planets than more massive stars. And we also know that low mass stars, including dwarfs, seem to have at least 2 different populations of stars when you look at the distribution of planet radius. So there are rocky planets and then there are non-rocky planets. And there's this so-called radius gap between them. And a couple of interesting questions that I wanted to look into because low mass dwarfs really haven't been studied very well. They're a lot fainter than more massive stars. So Kepler data didn't really allow us to study them in great detail. One of those questions is, does the occurrence rate keep going up as you go towards lower stellar masses? So our late dwarfs in particular, is that occurrence rate going to be higher than what's shown on this plot, which is once again predominantly based on early dwarfs from the Kepler mission? And then I was also interested in looking into what the radius distribution of planets looks like around low mass dwarfs. So I started with a sample of all mid to late dwarfs within 15 parsecs of the sun. But this is a well-defined sample compiled by Chen Winters. And it's limited to solar masses between 0.1 and 0.3. And there's a total of 512 stars in that sample, but I only took the ones that had TESS data in the first 42 sectors. So that's 365. And you can see these sort of the distribution of these stars in ecliptic orbits on the right. And obviously all of and as everyone working with dwarfs knows, these light curves can be very complicated. Dwarfs tend to have complicated rotational modulations as well as lots of stellar flares. So I did all of that analysis. And then I did a comprehensive planet injection and recovery for every single star in that sample, and characterized detection sensitivity as a function of radius versus orbital period up to 7 days. And there's a reason why it might seem a little arbitrary why I cut it off at 7 days. There were multiple reasons. One of them being that the TESS sectors are about 20 days, so that guarantees that I have at least a couple of transits per sector. But also the sample size is the 365 stars is small enough that the geometric probability of a transiting planet beyond 7 days gets so small that you wouldn't expect to see many planets to begin with. And obviously there are 7 known planets in that sample. Some of them were found before TESS using ground-based surveys like MERC, and others were found, or others were direct discoveries from the TESS mission. So I recovered all of these. And one interesting thing about these planets is the radii of these planets appear to be within this narrow range of 0.91 to 1.33 Earth radii, which I found interesting. You have 7 planets clumped together. And it is true that there's another planet we know of, there's GJ 1214b, which would have a period less than 7 days, but it did not have TESS data at the time that I conducted the study. However, it does not change the results of this analysis. So compiling the entire 365 stars, I can characterize the survey's detection sensitivity as a function of planet radius and orbital period, but also as a function of insolation, or the total amount of energy the planet receives from the star. And I would like to, so based on this, I modeled the underlying occurrence rate of planets. And I tested many different models, and this is all going to be described in a paper that should be published very, very soon. But I found that actually the underlying distribution is best modeled by a Gaussian distribution that's centered at roughly 1.1 Earth mass, Earth radii. And these 7 planets, the underlying occurrence is well explained by this model. When you sum up the entire sort of expected underlying planet occurrence, I find that roughly 61% of dwarfs have planets with periods below 7 days. And I can also place a constraint on the occurrence of larger planets, which is much, much lower, so at 7.2. And then I repeat this for insolation. What I would like to do now is to compare this work to a previous very well done study by Dressing and Charbonneau in 2015, which focused on early dwarfs from the Kepler mission. And there are some very interesting differences that emerge. So when looking at all the planets with orbital periods less than 7 days, the terrestrial planet occurrence actually does appear to be slightly larger than for earlier dwarfs. However, the large planets, water worlds, and the well-terrestrials, gas giants, all of these seem to be missing essentially, even when including 1214b, which is a very different planet distribution. And this is even more interesting when you convert to insolation, because stars of, planets orbiting stars of different masses get different amounts of radiation from their stars. So when you take that into account, the actually early dwarfs have about the same number of terrestrial planets as mid to late dwarfs. However, once again, the larger planets are missing. And I would like to highlight this ratio. So we estimate the terrestrial planets to be overabundant by about a 14:1 ratio over larger planets. Whereas for early dwarfs, you can see that these are roughly, the numbers are roughly the same. So I think this is a very kind of interesting result, that planets orbiting the smallest mass stars seem to be fundamentally different, at least for insolations larger than 4 times that of the Earth, so hot planets. And one last result I would like to comment on was the fact that, now that we've established that larger planets are really missing from around these stars, what can we say about sub-Earths? So there are no known planets with radii below 0.9 in the sample, but we do have some, or I do have some sensitivity over there. So what if I include this as a separate part of the model to essentially estimate how many sub-Earths there could be with radii between 0.5 and 0.9. And I actually find a substantially lower rate. So these are 1 sigma uncertainties, but the rate is different by at least a factor of 3, which is also interesting and probably, and does warrant further study with a larger sample size to confirm that. So to conclude, on average, mid to late dwarfs have 0.61 planets per star with orbital periods less than 7 days. And overall, this is consistent with early dwarfs, where there are fewer terrestrials, but more large planets that are missing for these low mass stars. However, when you convert this to equal stellar insolation, occurrence rate in mid to late dwarfs appears to be about a factor of 2 lower. So even though they receive the same amount of total radiation, low mass stars are known to have more XUV radiation, which might mean that the atmospheres around these planets are having a much harder time surviving, and most of them might be stripped compared to larger dwarfs. And in contrast to early dwarfs, the hot planet population is almost exclusively terrestrial around the smaller planets. And we estimate that this ratio is 14:1. And the occurrence rate appears to decrease for planets below 0.9 Earths. And this is something that I'm personally interested in studying more going forward, because I think as TESS data keeps accumulating, we will be able to study planets smaller than Earth in greater detail than ever before. So thank you so much for listening, and I'm happy to take any questions.
Do we have any questions to Kristo? One of you. So I'll just repeat, tell me if I got this right. Have you considered whether protoplanetary disks have an impact on the results?
Yeah, so this is actually one of the prime motivations for this study, because we know that stars of different masses have the protoplanetary disks also have are larger for more massive stars. And so far, there was this trend where actually, smaller stars tended to have more planets, somewhat counterintuitively. And this trend does not seem to continue towards the very low mass stars in this study. And I'm not, I haven't done any sort of underlying analysis of, or I'm not sure, what kind of mechanisms, in planet formation would cause that. But, that's definitely something that, the protoplanetary disk and the amount of mass that's available in there and the kind of planets that form in there definitely, is probably a key part of the answer to this question of, why do M dwarfs have more planets, and why do low mass M dwarfs not have more planets than high mass M dwarfs? So this is definitely an area where, where analysis is needed.
Okay. Okay, great. That's all for time. Thank you, Kristo. Okay, so we're going to move into a Zoom talk. I'm going to stop sharing, and then if people on the Zoom, I think we know who's next up. Could you share your screen? I'll stop sharing.
Hi, can you see my screen and hear my voice?
Yes, absolutely. So next up, we've got Tianjin Gan. He's going to go from South discovering giant planets and peoples. Just a reminder, we're on 7+3. We can't hear you. We can see your slides. Please take it away.
Okay, thank you. So good morning, everyone. My name is Tianjin Gan, a 5th-year graduate student from Tsinghua University. So I'm very glad to have a chance to present my recent works here. So today my topic is TESS discoveries of giant planets around the M dwarfs. So with the highest planet to star mass ratio among planetary systems, giant planets around the M dwarfs are the extreme cases to test the current planet formation models. Over the last 2 decades, hundreds of transiting giant planets have been detected. However, only few of them are orbiting M dwarfs. So as a full sky survey, TESS provides us a unique opportunity to enlarge this sample and further study their formation and evolution histories. So here I'm showing the planet to star mass ratio and semi-major axis distributions of all confirmed giant planets around the M dwarfs. And different colors in this plot represent planets detected by different methods. And in particular, these red dots with black circles are the TESS confirmed planets, which has already enlarged the total transiting sample by a factor of 2. And based on this data, we identified a possible paucity of hot massive giant planets around the M dwarfs, marked as a blue region here, where no planets are located in this area. And there is a potential trend of increasing number of massive giant planets as the semi-major axis goes up. And we suspect that these features could be a result of planet migration or two different formation mechanisms. And if this desert is true, and perhaps it could be reproduced by the theoretical formation and the migration models. But unfortunately, given the limited sample size of the transiting systems, these red dots here, this desert feature is still insignificant. So we hope that the future TESS mission could find more such planets and help confirm this paucity. And in addition, as a homogeneous survey, TESS also gives us a chance to look into the planet occurrence rate, especially hot Jupiters. So here I'm showing the hot Jupiter occurrence rate as a function of the stellar type. And different colors in this plot represent results from different works. And the dots and the squares in this plot are the measurements from the transit and the radial velocity surveys. So the horizontal uncertainties in this plot marks the range of stellar type used in each work. And for clarity, we add small shifts to the horizontal coordinates of some points to make the results more clear. And in particular, based on the TESS data, Zhou et al. 2019, these three gray dots on the bottom right, as well as Blesny and Kunimoto 2022, the three dark red dots on the bottom right, both found a correlation between a higher hot Jupiter occurrence rate and lower stellar mass. And it seems that this correlation could be extrapolated to low mass M dwarfs, although the previous three measurements on the M dwarfs are the upper limits given their non-detection results. So in order to test whether this correlation still works on M dwarfs, we constructed a magnitude limited early type M dwarf sample based on the TESS primary mission, which contains about 60,000 stars. And we detrained their QRP light curves and search for the transiting signals, as well as characterizing the detection completeness through an injection and recovery test. So finally, we obtain an hot Jupiter occurrence rate around the early type M dwarfs to be around 0.3%. So after adding these red dots in this plot, we find that the hot Jupiter occurrence rate tend to have a peak at G-type stars, and it falls toward both hotter and cooler stellar mass end. And finally, we also compare our results to cold Jupiters around M stars. But before that, for comparison, I'd like to show you the FGK results first. So here I'm showing the Jupiter-like planet occurrence rate as a function of the semi-major axis. So through long-term radial velocity surveys, Whitmire et al. 2020, these green squares, as well as Fulton et al. 2021, these pink squares, both found an occurrence rate transition at about 1 AU for giant planets around FGK stars. And this jump is probably related to the location of ice line, as the enhanced solid density beyond the ice line will facilitate the growth of a solid core inside the giant planet, according to the core creation theory. But what about M dwarfs? So these three dots here shows the results of M dwarfs. So combined with results from microlensing and radial velocity findings, these black and blue dots, we find that the occurrence rate trend of Jupiter-like planets around M dwarfs monotonically increased with a semi-major axis. And if the formation of giant planets around M stars is similar to FGK stars, and we would expect to see a similar occurrence rate transition around within 1 AU due to the lower irradiation of M dwarfs. However, given the limited occurrence rate measurements for warm Jupiters around M dwarfs with semi-major axis between 0.1 and 1 AU, even if this occurrence rate transition indeed exists, the exact turning point is still unclear. So we hope that a combination of TESS primary and extended mission, which could detect long period planets, could help address this question. So finally, here is my take-home message. So mass ratio and occurrence rates are two ways to understand the formation and evolution history of giant planets around M dwarfs. So that's all I have. I will stop here and happy to take any questions. Thank you.
Excellent. Thank you very much. What questions do we have in the beginning of our Zoom?
Sorry, unfortunately, I cannot hear the question very clearly.
That's okay. I'm going to repeat them.
Okay.
Do you see systematic differences between the radial velocity and the transit? Looking at the plots, it looks like they don't. There's always like a systematic process. Does that change the results between the end dwarfs and the non-dwarfs?
So the question was, is there a difference between the radial velocity and the transit? So it looks like there is a systematic difference for the end dwarfs and non-end dwarfs. And then
so are you asking about this plot? So sorry, I cannot hear the question very clearly.
The next slide.
The next plot, this one.
So can you hear me? Can you hear me now?
Yeah, sure.
Okay. So one more time. Yes. Yes. Okay, great. So is there a systematic difference between radial velocity and transits? And what impact does that have?
Yeah, so here in this plot, we can see that the radial velocity service always gives a higher occurrence rate on the hot Jupiter. So this is probably a result of close binaries, because for close binary, it could suppress the formation of circumstellar planets. And the previous works found that by removing the spectroscopic binaries from their RVs, the RV samples, the RV service for giant planets will boost the detection rates by a factor of 1.8. So this is probably a reasonable bias. Yeah. I hope that answers your question.
I'm getting nods, lots of nodding. So we're going to have to leave it there. Let's have one more round of applause for Tianjin. Okay, so next up we have Amy Tuson. Amy, if you're on Zoom, can you perfect? Thank you very much. We can't see your slides, we can see you. And so Amy's going to talk to us about a search for longer period transiting exoplanets with TESS and CHEOPS.
Yes, so hi everyone. Thank you very much for having me talk today. My name is Amy Tuson and I'm a final year PhD student working with Didier Queloz at the University of Cambridge. So I'm excited to tell you about my work, the search for longer period exoplanets using TESS and CHEOPS. So both of these satellites, they work in a complementary way to both discover and characterize transiting exoplanets. So whilst TESS is searching for new exoplanets, CHEOPS is a dedicated follow-up satellite that observes known exoplanets to learn more about them. So with that, let's now take a look at the planets that TESS has discovered so far. So here I've plotted the period radius distribution of confirmed exoplanets, where discoveries made by TESS are highlighted in pink. So you'll notice the entire population is heavily biased towards short periods, but the discoveries made by TESS are even more skewed towards shorter periods. So why is this? Well, it's a consequence of the TESS observing strategy. So TESS observes the majority of the sky for only 27 days at a time. So this means that it's much more likely to detect shorter period exoplanets. But it's now really important that we work towards expanding the sample of longer period planets to gain a more complete view of this exoplanet population. So I'm using TESS geotransits to do this. Now, a geotransit is a planet candidate with 2 observed transits separated by a large gap, typically 2 years. These are the observational signatures of longer period planets, but their true period remains unknown. So from the 2 non-consecutive transits, there exists a discrete set of possible period aliases. So you can use these aliases to perform targeted follow-up of the geotransit to recover its true period and ultimately confirm it as a planet. So you can see in this plot here is a simulated TESS geotransit and its period aliases in the right-hand panel, each of which has a probability. So it's typical that the shorter period aliases are significantly more likely than the longer period aliases. I'm a member of the CHEOPS geotransit program, and we use CHEOPS to recover the periods of TESS geotransits. Importantly, we are aiming to be complementary to ground-based efforts. So we only select targets for which space-based observations are necessary. So for example, if the transit depth is very shallow or the duration is very long. So how do we find TESS geotransits that we can then follow up with CHEOPS? Well, conventional planet searches aren't well optimized to find geotransits, especially the shallow, low signal to noise ones that we're particularly interested in. So therefore, I've developed a specialized pipeline to discover TESS geotransits. So my pipeline takes as input TESS PDC SAP light curves and outputs geotransit detections. So for example, if we take this star, on the left is the 2-minute cadence TESS light curve from the primary and extended mission. And then on the right-hand side, you can see the output from my pipeline, where you clearly see that 2 transits have been identified in the data. So the next step is to perform a visual inspection to assess whether the detection is likely to be real, and then it's ready for our follow-up observations. So if you're interested in more details of how this pipeline works, please feel free to ask me about it. So far I have run my pipeline on almost 42,000 stars, and it returned over 4,000 possible geotransit candidates. So what did I find during my visual inspection? Well, unsurprisingly, the majority of the detections were false positives, but this includes some eclipsing binaries and monotransits. But most excitingly for me, I found 5 new geotransits. So for example, here is one of these new discoveries. So on the left, you can see the TESS light curve from the primary and extended mission, and the pipeline detection is highlighted in blue. And then on the right, we have that set of period aliases. So this particular detection has a transit depth of about 400 parts per million. So this is one of the shallowest geotransits that we found so far. So here I've included the 5 TESS geotransits discovered by my pipeline on the period radius diagram from earlier. I've plotted them at their minimum period with a red line to indicate the range of allowed periods. So with the help of our CHEOPS follow-up program, I can now reveal that we have already recovered the periods of 3 of these geotransits. However, these geotransits are all orbiting stars brighter than a Gaia magnitude of 12. So let's remove all the confirmed exoplanets around stars fainter than this. You can now see that these geotransits are amongst the smallest, longest period planets orbiting bright stars. But this isn't all that we've done in the CHEOPS geotransit program. We have also recovered the periods of an additional 10 TESS geotransits. In total, we have discovered 13 long period planets, all of which have periods longer than 20 days, radii smaller than 5 Earth radii, and orbit stars brighter than a Gaia magnitude of 12. So there are only 16 other exoplanets discovered by TESS in this parameter space, so this work has almost doubled that sample. These small exoplanets on long period orbits around bright stars are really great targets for future follow-up observations to get their masses and look at their atmospheres. So I'm quickly going to highlight 2 of these discoveries that I'm leading. The first is TOI 461. This star was observed by TESS in sectors 4 and 31, revealing 1 periodic planet and 1 geotransit. So the geotransit in this system had 36 possible period aliases, and we have successfully recovered its true period with CHEOPS. So you'll have to wait for my paper, which is coming very soon, to find out what that period is. But for now, I can reveal that TESS and CHEOPS have discovered 2 mini-Neptunes orbiting this bright K-dwarf. The other system that I'm leading will remain anonymous because this one is not a TOI. This is the duo transit from my pipeline that I showed you earlier. So with TESS and CHEOPS, we have discovered a warm mini Neptune-sized planet orbiting a bright G-dwarf. We also have ongoing HARPS North observations to measure the planet's mass. So when combined with the radius, we'll be able to compute the bulk density and infer its composition. This will be a really exciting result. So on this plot are all confirmed exoplanets with a well-constrained mass and radius, orbiting a host star brighter than 9th magnitude. You'll notice that there are only 5 mini Neptune-sized planets with a period longer than 20 days. So our new planet will join this very small sample and help contribute to our limited understanding of mini Neptune composition. So I'll leave my conclusions here. I am looking for a postdoc position starting next fall, so please do get in touch if you know of any opportunities. And thank you very much for listening. I'm happy to take any questions.
Okay, apparently there's some feedback on the mic and it's making it hard to hear, so I'm just going to shout. Thank you, Amy. Do we have any questions for Amy in the room or on the Zoom? You do? Me, Andrew?
So this is very cool. If you have a strategy for which transits you observe, can you choose to observe one and lose out all period ratios that are multiples of 2, or one that are all period ratios of multiples of 3, etc.?
So I'm going to repeat to the best of my ability. First off, great work. The question was, does CHEOPS have a strategy for minimizing how much follow-up is done for these planets? Do you, for example, rule out transits or use transits that are going to rule out factors of 2 and then factors of 3?
Yeah, so if we have a look at this plot, for example, with the period aliases, we rely upon these probabilities typically. So what we'll do is we'll schedule these kind of top probability aliases. And if we don't see a transit, then we will perhaps move to the slightly lower probability ones. But in our experience, we find that the period is very normally in this very high probability regime over here. So we haven't really had an issue yet with not being able to recover a transit after many observations.
Okay, great. I've got another question in the room from George.
Yes, this is a very interesting result, Amy. One of the things that would be interesting to know would be as EM2 progresses, you will have a chance to look at these objects again. And so for that home of possible period aliases, have you made an estimate of how many of those aliases will be eliminated?
Amy, do you mean to repeat that?
I heard that one. That's right.
Okay, great.
Yeah, so that's a really good point. Yes, with the TESS extended mission, we do expect that quite a few of these duo transits will transit a 3rd time. But the interesting thing that we found with some of our predictions for the particular duo transits that we're looking at is that in some cases, we won't actually gain any more information from the 3rd transit, because it might be that it is exactly separated by the same length again. But in some cases, we will gain much more information, in which case there will either be a few aliases remaining or it will be entirely resolved. It completely depends on, obviously, the period of the system and when the next observation falls. But it'll leave us with some of these trios that we will start coining. So trios will become these planets that have 3 transits, but still an ambiguous period. So they will still be something that CHEOPS will be able to consider in our own extended mission for continued follow-up.
Fantastic. Awesome. Okay, I think that's about the time we have. Let's thank Amy again.
Thank you very much.
Okay, next up, we've got Luisa Maria Serrano. Luisa, if you're on the Zoom, can you share your screen? And Luisa's going to talk to us about the HD 93963A system, which is a 1-day super Earth and a 3.5 sub-Neptune discovered by TESS and CHEOPS.
Yes, can you see this?
Luisa, we can see your screen, we can hear you. Please take it away.
Okay, this is good. So Thank you very much for letting me presenting this great work. This is the result of a contribution from both TESS and CHEOPS collaborations, but also from the teams of other instruments such as SOPHIE, Muscat2, SPIRou, Allopec, ESPRESSO. I want to remind you that all these works are results of the contribution of several people that are actually putting a lot of effort in this. So the story begins with a long time ago, well, not a very long time ago, but actually when I entered the CHEOPS team, I presented a program in order to observe targets that would appear as transiting like signals within the TESS light curves, and that were below the signal to noise ratio chosen by the pipeline from TESS for the selection of the TOIs. So this is what I did was, we have CHEOPS, we have another instrument that allows us to observe transits, and that allows us to improve the precision on the radius if possible. So maybe we can validate some targets that TESS might take longer to observe or something like that, or that TESS cannot validate because they will not reobserve it anymore. And among our golden targets, there was HD 93963, alias TOI 1797. So at the time, we only had TESS sector 22 data. And although we knew that another sector we observed, in reality, we decided to observe it anyway with CHEOPS, because we thought that being this an active star, it would have been more complicated to validate a target, a signal like this. So the TOI within this system was a 3.65 days target, while we found an additional 1.04 days signal with a signal to noise ratio of 6.7. And we analyzed very quickly the light curve, and at the time we didn't have precise values for precise ephemerides for the so-called choice CHEOPS object of interest. And so we decided to observe it with just a 1.4 days continuous follow-up in order to cover an entire day, and somewhere during the day the transit happened. So this is what happened, that we observed it, and in reality our predictions revealed to be very precise. We could see the transit more or less in the middle of the visit. And so the transit was real, we could validate it, and we decided to continue observing it, collecting a total of 8 visits for the USP planet and 1 for the TOI planet, until we reached that a 3% precision on the radius. And in the meantime, we got data from SOPHIE for stellar analysis. And what we know about TOI 1797 is that it is a G0V star, very similar to our sun, but slightly younger and with a similar composition than our sun. So the period of rotation was a bit of a debate at the beginning, but it is around 10-13 days, because we see patterns in the TESS light curve that are more or less at 6.5 days, but then they repeat themselves only after 12 days. So it means that there are spots probably one behind the other in the same hemisphere in a sense. And then we also got observations from FARO who confirmed the presence of a stellar companion at 6 arcseconds, but our validation process allowed us to exclude that the 2 transiting candidates were for sure around the primary star, so around TOI 1797A. And that's it. So then we performed an analysis on the CHEOPS data, considering background and roll angle as the trending parameter, removing outliers. And then we also considered linear and quadratic trends, because the star is active anyway. We joined this with the TESS data, with the trended TESS data with Zitlalik, and then we performed the joint fit with Pianetti, just for just as an elegant plot, I show you the joint feet that are here in this slide, and you can see that the transits are well detected both in TESS and CHEOPS. In addition, I can say that one planet, the smallest, is extremely similar to our Earth in terms of size, 1.3 Earth radii. The other one is 3.2 Earth radii, so it is a Neptune-like planet. So the smallest planet is a USP, is likely to be a USP. The other one has a period of 3.64 days. And these details are important because if we want to explore also for future interest the structure of the system, the architecture of the system, we have to take this into consideration. We had some data from radial velocity follow-up, but that was not enough to have to allow us to perform a joint fit with radial velocity. What we could do instead is identifying, first of all, a linear trend, so a long-term trend in the data, first of all. And in addition, we could say that once we knew that the planets were validated, we could extract them from the data and we could confirm that the period of rotation was close enough to our prediction of 10-13 days from the TESS light curve. Finally, what I can say is that the planet C is likely to be a 19.2 Earth masses planet, while for the other one, we have less information because in any case, while it is detected, it is lightly detected. The error on it is on its mass is still very large. But we can say that it should be around 2.4 Earth masses, also considering theoretical extractions. So what is interesting about this system is that we have planet B and planet C on the two sides of the radius valley, which means that they had different history on photoevaporization. And we did perform an analysis on the photoevaporization, and while planet C should have a consistent atmosphere, planet B is of course a USP planet and is completely stripped of its primary atmosphere. So it's supposed to be a nude body, a naked body orbiting its star. Finally, what are the possible considerations we can do on the formation of this system? Actually, we don't know, because the presence of a companion to this planet, to the main star, tries to mess up a little bit what we might know on the formation of USP planet. We could say that there are secular formation processes behind, and that the process of formation is similar to the one predicted for CORO 7b, for example, because the structure of the system is similar to the one of CORO 7b actually. So a low eccentricity model with planets that formed on quasi-circular orbit and then just migrated in a quasi-equilibrium state until they reached the final equilibrium state. But this is not for sure, because as I said, the external star messes up things, so it has to be tested in our recent paper on TESS 500. So to conclude, what we should do is getting new data, and what we are actually doing is getting new radial velocity data for this system to try and understand better the migration process. So this is still ongoing, and thank you very much.
Excellent. Thanks very much, Luisa. Do we have any questions in the room or on the Zoom? Probably got time for one quick question. Oh, yes, perfect. Andrew. I'll repeat. Have you investigated the orbit of the wide binary companion?
I didn't understand. I'm sorry. I didn't get the question. I didn't hear the question.
Sorry, let me say again. Have you investigated the orbit of the wide binary companion?
The orbit. Yeah, we know that it is at around 484 astronomical units from the main star, but we don't know much more. We have one observation of it that we still need to analyze, but we will know more later.
Okay, fantastic. Thank you. Let's thank Luisa again.
Thank you.
And then we're going to hear from Solene Ulmer-Moll. Solene, can you pop your talk online if you have it? Perfect. And Solene is going to talk to us about TESS single transits characterizing warm Jupiters. If you're ready, we can see your slides. I think we can hear you. Take it away.
Thank you. Yeah, so I'm Solene Ulmer-Moll. I work at the Observatory of Geneva with Monica Lendo and Christophe Mondazzini. And I will talk about transiting warm Jupiter and how TESS is helping us to find more of this kind of planet. And of course, this work is done in collaboration with mainly the TSTPC group led by Diana Dragomir and the NGTS team. So I will start by saying that actually few transiting warm Jupiter have been detected so far. You see here the radius versus orbital period of planets with precise mass and radii measurement. And I circled in orange the type of planet that I'm interested in. So usually around Sun-like star, the warm Jupiters have a period larger than 20 days, and I'm interested in massive planets, so gas giants. And an interesting fact about this population is that they have a wide range of eccentricities. So you see in red the hot Jupiters, which have relatively low eccentricities, probably due to star-planet tidal interaction. And on the right side, you have the warm Jupiters, circled in orange, that cover a wide range of eccentricities. And it's still unclear how this kind of planet form and evolve. For example, there could be a hot Jupiter in the midst of high eccentricity migration. And that's why we observe them with these high eccentric orbits. Now, if we look at the gas giant that we know best, the ones in our solar system, we know that Jupiter and Saturn are metal enriched. And basically, this warm Jupiter can be the link between hot Jupiters and the core giant of the solar system. So Jupiter and Saturn have an abundance ratio measured for various elements, and Uranus and Neptune are even more metal enriched than Jupiter and Saturn. And we can ask what happened for extrasolar gas giant, and are they metal enriched, and is this metal enrichment correct with the host star, for example? And this is a work that's been done with by Thorgan et al. 2017, where they studied about 50 transiting warm Jupiters. And they noticed that the planet metal enrichment correlates with the planet mass, is the plot that you see on the left side. And they also show that heavy element mass correlates with planetary mass. And on the right side, I show a plot from Paul Darba et al. 2022, where the author investigated the dependence on orbital period of this relation. So the planet metallicity is anti-correlated with the planet mass, as for Thorgan, but they show that for longer period planet, longer than 100 days, we see a hint that there could be two different slopes, and maybe the scatter of this relation could be different too. And so these findings are broadly consistent with core accretion models, and they actually give us information on the type of accretion that happens in the protoplanetary disk, for example. So it's interesting to refine this mass metallicity relation. And to do that, I use TESS, and warm Jupiter appear as monotransit in the TESS data. So you see here two plots of two different sectors of TESS data. On the first one, I highlighted a single transit event in blue. And when TESS reobserved the same field 2 years later, we didn't see any transit. So we need a lot of follow-up to try to confirm this type of event. And for that, I use first a broad vetting on the light curve, of course, to exclude EBs or asteroid crossing. And then we look at spectra to try to find out if the planet is true planet, or it could be a spectroscopic binary, for example. Then I also use CORALIE and HARPS to measure the mass of these companions. And we need photometric observation to recover the period with certainty. So for example, with TSTPC, we use the LCO network, but I also collaborate with NGTS, where they have a dedicated working group to hunt these monotransit events. And of course, as you heard from Amy, CHEOPS is doing a lot of work on recovering these long period planets, but the smaller ones. And so I want to show you just one example of transiting warm Jupiter. On the left side in orange, you have the TESS single transit that I showed before. Then NGTS was able to recover a second transit. And from that, we then schedule period alias chasing, where we only observe the night where we know a period alias can transit. And we recovered a third transit, solving the orbital period of that candidate at 54 days. I also acquired a radio velocity with the CORALIE spectrograph and collaborators at Pharos and Chiron RVs. And we were able to measure the mass of the planet at 3 Jupiter masses on a quite eccentric orbit of 0.4. And this is just one of several planets that we have detected with this survey. You see here that we have a couple of multi-planet systems, a very eccentric one at the top middle panel, and also quite long period ones with 75 days or even more than 100 days. So it's a lot of new exciting discoveries. And what can we do when we have the mass? Well, we can go back to this planet metallicity estimates. So here I showed the radius as a function of time, modeled with a planet evolution model. And the different colors represent different metallicity of the envelopes. And basically for that planet that I showed before, NGTS 20b, we were able to show that the planet metallicity is 6 times higher than the stellar one. And this corresponds to a mass of about 100 Earth masses of heavy element. And actually, in terms of planet formation, this large amount of heavy elements is a bit challenging to explain. So there are different scenarios that can generate that amount of heavy element, but it's still a subject of research. And so to conclude, after 1 year of observation and program on HARPS, we detected 10 new warm giants. So it's about a 50% increase on this population of transiting warm Jupiters. I showed them in a mass versus period plot, and in red diamond, you have the new detection. They are not all published, but we are working on them. And the next step is, of course, to study the bulk composition of all these new warm Jupiters and to try to refine the mass metallicity relation. So thank you. I'll take questions.
Excellent. Do we have any questions for Solene in the room or on the Zoom? Yeah, one online. Do you want to, maybe I can read it out. So Joanna Test asks, what is the TF effective range of the host stars of these new warm Jupiters?
And they are between K and F stars. So I would say maybe not lower than 4,500, I think. Yeah. Yeah, of course, we can also look at the stellar metallicity and abundances and try to refine the relation like this, since it's, yeah.
Excellent. Any more quick questions in the room? If not, thank you very much, Solene. Thanks, Solene, again.
Thank you.
And then Elisa Goffo, if you're online, would you be able to share your screen?
Yes, sure.
Perfect. And we can hear you and we can see your slides. Elisa's going to talk to us about ultra short period sub-Earth. Do you want to take it away, Elisa?
Thank you. Thank you so much for having me today. I'm Elisa Goffo. I'm a PhD student working in the University of Torino and at the Thuringia Landessternwarte of Teutoburg. And today I'm going to talk about the new results that we obtained from a radio velocity follow-up campaign about the system GJ367. So first of all, the star was observed by TESS in 2019, and last year, Lametol, they discovered a dense ultra-short period sub-Earth planet transiting M dwarf star. This planet is orbiting the star in 0.332 days. It has a mass of 0.55 Earth masses, a radius of 0.70, around 72 Earth radii, and a density of about 8 grams per cubic centimeter. From interior structure models, they predicted that the planet has an iron core radius fraction of 86%. So, as I said, TESS observed the star in sector 9 in 2019, and they observed the star to confirm the planetary nature of the transiting signal with ARPS spectrograph, obtaining 77 radio velocity data. But in the previous analysis, there was also a tentative detection of a signal at 11 days. So to study this signal and to understand the architecture of the system, we continue observing the star with HARPS, obtaining more than 290 new radio velocity measurements. And in the meantime, TESS observed again the star in sector 35 and 36. So to see which signals are present in our ARPS data, we perform a frequency analysis, and we found two significant signals, one at 11 days and the second at 34 days. These two signals, they don't present any counterpart in the periodograms of the activity indicators. And this provide evidence that these two signals are caused by the presence of two other planets in the system. In addition, we found the significant signal at 0.32 days, confirming the planetary nature of the transiting signal, and other two significant signals at around 50 days and 130 days. But for these two signals, there are present in the periodogram of the activity indicators. So this suggests that they are likely associated to stellar activity. So here briefly, just show the plot of our light curves modeling for the inner transiting planet for our radio velocities data. And those are the results that we obtain with all the new data. So for the inner planet, we refine the planetary parameter. We found now a mass of 0.63 Earth masses, a radius of 0.7 Earth radii. We improved the precision and we found a density of about 10 grams per cubic centimeter. As I said, our HARPS radio velocity measurement also revealed the presence of two other companions. So one other planet at 11 days with a minimum mass of about 4 Earth masses, and a second planet at 34 days with a minimum mass of 6 Earth masses. Reporting here the mass radius diagram of the ultra-short planet smaller than 2 Earth radii. GJ367b is the smallest and densest planet, USP planet, with a mass and radius that are known with a precision better than 15%. So regarding this ultra-short period planets, this very interesting exotic class of objects, there are like a lot of theories to explain the formation scenarios, the origin of these objects. And so they are believed to be the remnant naked cores of Neptunian planets that lost their atmosphere during the migration processes. But we still don't know how these planets reach the current short orbit. So there are some secular formation theories. These theories are like the highest centricity migration scenario and the lowest centricity migration scenario. In one case, for the highest centricity migration scenario, we considered the presence of an inner planet with a orbital period of about 10 days. and the presence of other companions in the system. And for secular interaction, the inner planet reach very high eccentricity and will approach this host star very close enough that it will be tidally captured, and we reach a final orbit, very short and circular orbit. In the other case, for low eccentricity migration scenario, we consider low mass planets that have initial orbital period of few days. We consider very mild eccentricities in this case, and the inner planets so will go to an orbital decay due to tidal dissipation. So as was done in for the discovery and in the discovery paper of TOI 500b, we tried to see if we can explain the architecture of the system through a low eccentricity pathway. But so what we discovered from our models is that it's hard that for this our inner ultra-short period planets to reach the current orbit, this to migrate in this very distance, and so it seems that after 5 gigayears the planet cannot reach the current orbit considering this pathway. So to conclude, we refined the planetary mass and the radius of the USP planet GJ367b with an intense ARPS radio velocity follow-up campaign. We discovered 2 additional long-transiting planets at 11 and 34 days. We tried so to see if we could explain this architecture to a low eccentricity pathway, but it seems that this architecture can likely be explained more via a violent migration scenario. And finally, I would like to highlight the fact that these long-term radio velocity monitorings are fundamental to explore in detail the migration processes that can account for the architecture of systems hosting US ultra-short period planets. And that's all. Thank you.
Excellent. Do we have any questions in the room or on Zoom for Elisa? Okay, we've got one from Andrew.
So how do you make a planet purely of iron?
The question was, how do you make a planet purely of iron?
Yeah, this is an interesting question, and it's something that we still don't know. So it would be really interesting to know how we can form really a planet made just of iron. But yeah, maybe with further studies and analysis would be interesting to know.
Excellent. Okay, so I think, thank you very much. I think we do have to move on, unfortunately, to our next session, but thank you very much for a really interesting talk. Let's maybe thank Elisa and all our speakers. Okay, so thank you again to all our speakers online and in person. We're gonna hear from Dave now in the next session.
Okay, now we're going to shift gears. Yes, I bet it's loud enough. So I organized this session for the very precise radio velocity teams to be in the morning of the second day, because there are a lot of European teams that are contributing, and I didn't want to have them stay up all night in order to make their presentations. So there are more than 24 teams that are contributing to the mass measurements that allowed us to meet our level 1 requirement of more than 50 masses of planets smaller than 4 Earth radii. And now that the first extended emission has just about doubled that, I think it's 99 or 100 masses are now in the public domain. I wanted to give the teams that belong to SG4 a chance to talk about their work. So I have 16 of the facilities represented here by 13 presentations. We're going to keep this to at most 5 minutes apiece, but I wanted to give people a chance to talk about not only their own work, but about some of the other teams using the same facilities. So I am going to give you a 1 minute warning after 4 minutes. And I'd like to save the questions to the end because that'll slow us down and you can ask questions at the end. So save up your questions until the end. So Norio is not in Europe. Norio is in Japan. That's why he's right at the top here. Go ahead and share your screen, Norio.
Okay, I'm already sharing my screen. Can you see my screen?
Yes.
Okay. So can I start?
Yes, please.
Okay, so I'm Norio Narita from University of Tokyo, and I'm leading a project to follow up test discovered planets around mid-rate M dwarfs with SPIRou IRD. So first, I will introduce about SPIRou IRD. And IRD is on the SPIRou 8.2 meter telescope on Palle, Mauna Kea, and it is a stabilized spectrograph with spectral resolution of 70,000 and covering wavelength is Y to YJH band. And it's combined with mode scrambler and also the laser frequency comb, and it is stabilized. And this is expected velocity precision for different types of stars, for different stellar temperatures, and also the different stellar rotational velocity. And as you can see, for the M dwarfs, say less than 3,500 Kelvin, IRD can measure the radial velocities with less than a few meter per second precision. So we are using this instrument for mid-rate M dwarfs. And as you know, that TESS has discovered more than 100 TOIs in a few years. And about 50 TOIs are observable from Mauna Kea. So we proposed an intensive PRB follow-up project with SPIRou IRD. And we were awarded about 50 nights SPIRou time and until this semester. So I just pick up one previous result for two USPs, say TOI 1634b and TOI 1685b. So we could measure the precise masses of the two USPs. And also this is for Earth-like planets, but now our current interest is moving on to the slightly larger planets, say close-in giant planets or low-gravity small planets, say with high TSM or temperate planets. So I just pick up two ongoing work to show our recent work. And one is now submitted by Taiki Kagetani. And this is a giant planet, a closing giant planet around the mid-M dwarf, that is TOI 590b. And we measure the mass with IRD, and it turns out to be half of Jupiter mass planet. And it is orbiting among the lowest temperature host star. So this is very interesting. And also we measure the metallicity of the host star with SPIRou IRD and also collaborating with IRT specs team. And it has a high metallicity. So this paper is already submitted, and once accepted, we will show you in archive. And also we are observing several sub-Neptunes. And actually, we have not yet published many papers, but this is one case, TY 654. And actually, we observed this target for 4 years. and we already get very low for sudden probability for the period of the transiting planet. But as you can see, that's the residual for the planet model has very noisy and also the systematically away from zero. And we found several possible outer planetary candidates. So we are now still struggling to determine the second planet period. So yeah, but we are for this semester, we will end the current project. So we are now proposing an extension of this observation. So stay tuned for a new result. That's all. Thank you very much.
Oh, he's right on time. Excellent. Next, Francois Bouchy will talk about ESPRESSO and CORALIE. Share your screen. Norio, thank you, but unshare, thanks. Here we go. Go ahead.
Okay, thank you very much, Dave. So let's start with CORALIE. So on CORALIE, we dedicate typically since the beginning from 30 to 40 nights per semester for the TESS follow-up activities. Our main programs now, main priorities are clearly so there is giant candidate orbiting hot stars. There is also the long period giant candidate following monotransit, duotransit. We are also doing a long-term monitoring to search for outer companions, including a short period transiting planet. And we are also giving support for the vetting of candidates for ARPS program, ESPRESSO program, and soon NIRPS program. I wanted also to add that we regularly are doing some release of radial velocity from CORALIE, and so far we have more than 100 TOIs released on the DAYS platform. And we should expect to have a new release maybe for Christmas this year. So a few results from CORALIE. Some of them were already presented by Solene Ulmer-Moll a few minutes ago. So a giant planet at relatively long orbital period, but also a giant planet orbiting hot star. This is a program led by Angelica Psaridi. Or brown dwarf, also transiting brown dwarf around hot stars. A result here of a Jupiter mass object at 75 days, published by Nolan Greaves, and also eclipsing M dwarf close to the hydrogen burning at 30 days period. On ESPRESSO, so ESPRESSO is really focusing on the ultra high precision, radial velocity precision. So there is still the ongoing GTO program led by Francesco Pepe, who we dedicate typically 10-12 nights per semester for the follow-up of transiting planet, focusing on the rocky population. So it means candidate below to Earth ready, but also probing the sub-Neptune parameter space with irradiation between 50 and 200 times the Earth insolation. But there is also a ESPRESSO PI program. I'm leading a program. I'm focusing on the warm mini Neptune orbiting a solar type star. Nolan Greaves is focusing on a sub-Neptune orbiting M dwarf. Lily Box obtained a time on LHS 1140. Nathan Hara did some measurement, precise measurement on the multiplanetary system TOI 178. Van Allen, Bonfils also has some ongoing program on ESPRESSO. So this is a mass radius diagram with some highlight from ESPRESSO. Let me show you some very recent results. Susanna Barros published 5 planets detected by TESS and characterized by ESPRESSO, multiplanetary system around TOI 174. Batislavi, we reanalyze also, and we obtain many more ESPRESSO data on TOI 455, including a third non-transiting planet. So it should be soon. I mean, the paper is accepted. It should be on archive in a few days. And then we submitted recently sub-Neptune orbiting the K dwarf star TOI 262 by Maria Zapatero Osorio. And I would like also to give an advertisement about NIRPS. So NIRPS is in Latham presently, is joining ARPS on the 3.6 meter telescope. and it's now opened to the community. So the first proposal were submitted end of September. We expect to start operation in April 2023. So for period ISO period 111, the NIRPS consortium will benefit of 725 nights over 5 years of guaranteed time. And we already protected 81 test targets for the work package 2 devoted to the mass characterization of transiting planet for the first year of GTO, to dedicate 45 nights for this program. So, and this is preliminary result obtained during the first commissioning. So without theory correction, without optimization of the mask, correlation mask, etc. But at least it's very promising. We have on typical standard stars like the Barnard stars, Proxima, at the level of 3 meters per second. It's preliminary result. We have still several commissioning in the coming month. Thank you very much.
Terrific. Thank you, Francois. Okay, next, Davide Gandolfi, representing the KESPRINT consortium that uses every telescope on the planet. Davide, go ahead and share your screen as soon as we unshare.
Can you hear me, Dave?
Yes, I can hear you fine.
All right. Good morning, good afternoon, everyone. So let me start the presentation. Hope there is nothing on top or in front of the
Looks good.
Slides. All right. Okay. So I will be talking about the KESPRINT follow-up of TESS transiting planets. So I'm talking on behalf of a big consortium. So it's not moving. Can you hear me?
Yes.
All right. Okay. It's not moving. Okay.
It's moving. Yes.
Yeah. Right. So it's a big consortium. We are almost 50 people coming from all over the world. Basically, we got collaborators in the US, mainly in Europe, and also in Japan. And we do radial velocity follow-up of transiting planet, mainly radial velocity follow-up of transiting planets. We use different facilities. We use moderate precision radial velocity facilities to follow up or hot Jupiter, or to vet small planet candidates. And I show you here a family portrait of system that we publish based on this moderate radial velocity, moderate precision radial velocity facilities that we published this year. And then we also use high precision radial velocity facility to observe small planets. And let's put this one here. And it's so we see we have different facility in the northern and the southern hemisphere at different longitudes. And since I'm coordinating the HARPS follow-up, I will be talking mainly about HARPS. So we had two consecutive large programs covering a baseline of 4.5 years. So we got 78 nights from 2018 to 2020, and we got another 96 nights from 2020 till March next year. You see, usually it's 2 years, 2 plus 2 is 2.5, simply because of the pandemic. We got some compensation time, which of course has extended our baseline, but has also delayed the follow-up of small planets. So we do, the goals of those two proposals is the confirmation of TESS small planets, the determination of masses to a precision better than 15%. We are really focusing on ultra short period planets and planets near the radius cap. And thanks to this long baseline, we are also unveiling what I like to call the intermediate architecture of systems hosting closing small planets. So up to, I would say, a couple of AU from the host star. We collect nearly 3,000 spectra, and we observe about 35 TESS FGKM stars. So some highlights. So one result that we published recently in a paper led by Karina Persson is DOI 2196, which is a USP planet, 1.2 days. So it's almost USP planet. Is a hot Neptune in the hot Neptune desert. It's pretty much massive. And intriguingly, we found that there is a clear linear trend that is consistent with the other massive companion. This star is currently under observation with HARPS to pin down to get the Keplerian orbit of the outer companion. Then TOI 1130, which is one of the juicy target, was discovered by TESS, an announcement paper led by Chelsea a couple of years ago, which is a WOS47-like system. So you have a hot Jupiter on an 8-day orbit and an inner Neptune on a 4-day orbit. And the two planets are very close to the 2-to-1 period commensurability. And this is causing very strong TTV, as you can see here. So we follow up this target with HARPS, and we collected 50 measurements and put them together with 20 PFS measurements taken by Sam Quinn and collaborators. And we nicely got the mass for the inner planet, which is pretty much a Neptune-like planet with a precision of 4%. And we also clearly detect a linear trend in the data. And of course, this system is still under observation with HARPS because we want to get the mass of this outer companion. Then TOI 1054, which is a paper led by Juan Cabrera and will be submitted relatively soon, which is a warm Neptune. We observed with HARPS, and once again, thanks to the long baseline, we discovered that there is an additional planet, which is a Jovian companion on a 300 days orbit. And this target was also observed by CHEOPS. Then also I would like to highlight the paper we recently published in Nature Astronomy is led by Luisa Serrano, and is TOI 500, which has a USP planet on a 13 hours orbit. And once again, 200 HARPS measurements, and we detect three additional planets. So you see them here. And actually, we really track down the architecture of the system up to 600 days from the start and orbit period, which allow us really to assess that this planet might have, this system might have formed through a low centricity migration scenario. So just to summarize,
okay.
So those are the papers we published so far, the number of papers we published so far, this number of systems we have observed, and we detected a number of non-transiting planets, and we also detect additional transiting planets that have not been found by TESS simply because of lack of photometry, and will be announced soon, and thanks to CHEOPS observation. And I just something I did this morning, this European morning, and I was just counting the number of systems we observe in which we detect outer giant planets. And we found, and what I found is roughly an occurrence rate. So you simply divide the number of systems we observe, for which we have gas giant planet, divided by the number of systems we observe. And I got like 35% of the system have an outer gas giant planet, which would be an agreement with previous estimates. I support here a paper that clearly says that planets hosting close-in small planets are very likely surrounded by an outer giant planet. And that's it.
Okay, we need to finish up. Great. Very impressive, Davide. So we gave you an extra minute.
Thank you.
And but Enric, why don't you tell us about teams using CARMENES and what you guys are doing?
Thank you very much for the opportunity. Today I'll be talking about. Today I will be talking about the CARMENES TESS program on behalf of the CARMENES consortium. Just to do a brief introduction, CARMENES is a visible and near-infrared spectrograph, which started operations in 2016 and enjoyed a really large GTO time at the telescope. And I think that these two things, the early start of the spectrograph just before the TESS era and the large number of observations available, has allowed a very rich program of observations, which is all focused on M dwarfs. So it has three main programs within the GTO. One of them is the blind search for planets around M dwarfs, of which I will not talk about, but is the main goal of the GTO. The other one is to exploit this really nice synergy between TESS and CARMENES, because both instruments are really well suited to find planets, transiting planets around M dwarfs. And it's obviously not only CARMENES, there's other spectrographs that do that, but we have really exploited this synergy. And then we have also used the near-infrared arm to look for signatures of atmospheres in some exoplanets. I'm not going to show individual results because I have only 4 minutes, so I'm just going to give you this slide where we show the number of known planets around M dwarfs And you can see that CARMENES has discovered every 3 planets, 35% of the known planets that transit around M dwarfs have had their masses measured by CARMENES. This is a slide is 1.5 years old. We have a few more discoveries. The number is probably around those lines. And what is interesting is that planets around M dwarfs, especially around bright nearby M dwarfs, are really interesting because these are the top priority targets that will be exploited and by JWST and the ELTs when they come online. In fact, the majority of our targets that we have detected on bright stars with CARMENES are already part of the GTO or are included in GO programs. And CARMENES, so here you have a graphic of the transmission spectroscopy metrics and emission spectroscopy metrics of all small planets below 5 radii of the Earth. Blue ones are around other stars type, red means around M dwarfs, and the stars are the planets that have been discovered by CARMENES. And what you can see is the sweet spot for CARMENES is the detection of planets with radius between 1 and 2 radius of the Earth. If we do a zoom on the really small planets, with radius smaller than 1.5, you can see that CARMENES has really found a wealth of planets that are really suitable for transmission spectroscopy and also for emission spectroscopy metrics. And the new one is GJ806 that is about to be published next week. We hope to send a revised version to the referees, and which is so far one of the best targets for transmission spectroscopy and the absolute best for emission spectroscopy metrics on a small rocky planets. But more important is that the fact that there's this synergy between TESS and the ground-based radio velocity spectrograph that enables us to have mass and radius, and that allows us to do a more informed demographics, and that allows us to publish a paper recently where we revise the mass and radius of all known planets around M dwarfs and start to categorize these planets. We speculate here that well, we don't speculate, I think we demonstrate that planets that at least around M dwarfs, the radius gap is not produced by photoevaporation, but it's really a density gap that responds to composition at the time of formation and migration of inner planets. So we have planets that are Earth-like in composition, and we have planets that are water worlds with up to 50% of their composition made of water. I also want to use one slide in 30 seconds to talk about the potential of CARMENES for characterizing some of these planets found by TESS and by other surveys. And one of the nice things we can do is have line detections of the helium line. This was one of the first spectrographs that was able to measure those lines from the ground. And thanks to that, we have found evidences. We have measured this on a dozen planets, and we found evidences that there are 3 theoretically predicted escape regimes, and we found planets that agree with those on all 3 of them. And there's a very recent paper from Lampon et al. Last year that summarizes this. If you want to see a taste of what comes ahead, these are the TOIs that have been recently published in the last year by CARMENES team. These are the targets that you will see appearing on AstroPH in the next months, because we have detections and we are nearing different stages of nearing the, yes?
Okay, thank you.
Yeah.
Next up, Dave Armstrong has a bunch of consortia working with HARPS with big programs. Tell us about that, Dave.
Yep. Can you hear me fine and see that?
Looks good.
Great. So I'm covering the HARPS spectrograph. This is a high precision optical spectrograph capable of going down to meters per second precision in small planets in the best cases. As with Davide, there are many, many, many people involved in this, so I haven't even managed to fit them all on a slide. So please don't be upset. There are several programs involved on this. There have been many going since the launch of TESS. So the 2 biggest ones are my one, which has been called NCORS or Nomads for quite a while, and the KSPRINT program you've already heard from Davide, so I won't say anything else about that. They're in the current semester, so starting this October, there's a 12-night program by Raphael Brahm and several others that have been going since. Brahm was unfortunately not able to give an update thanks to health issues, but I've got some other programs we'll talk about. Overall then, since the TESS launch, there have been pushing up to about 100 nights a year on HARPS dedicated to following up TESS targets. Since then, there have been well over 50 low mass planet measurements, so it's really been an effective spectrograph. They've asked me to tell you a bit about how the HARPS time is organized as well. So many of these programs, most of them actually share time throughout each semester. So this gets organized in, well, you can see about 70–80% of the time. That has a whole load of advantages. It means this 20-night program that I'm running can have observations spread over, well, essentially the entire semester. So we can track long-term orbits, we can optimize the LV observations, we can use fewer observers, which is better for the CO2 footage, of course, and we can share things like the weather risk. Now that has a huge amount of organizing, so thank you, Francois, for doing a lot of that, and Xavier as well. And you can see, I don't want people to stare at this, but you can see the complex spreadsheets that are involved. But it does tend to work, and it works very well. Now, looking at these programs, this is the first part of my program that I want to talk about, the NCLES one. It was active from basically the launch through to 2021. This got a total of around 70–75 nights, and you can see there are 26 planets shown here that were detected and characterized mostly in the level 1 planet regime. There are several more still in prep, so this is coming up to a total of well over 30 by the time they all come out. Now, these are all TFOP planets. Many of them are joint with other teams. You can see some non-transiting planets shown in orange on the right there. I just want to, given the short timescale we've got, highlight a few key ones. I've linked the ones in multiple systems here with dashed lines, so you can see several nice multiple systems. TOI 125 is a chain of 3 nice super-Earths in resonance orbits with strikingly different densities, so a nice formation puzzle for people there. TOI 431 is a 3-planet system, one of them non-transiting, with an ultra-short period small planet and another one on the other side of the radius gap, so a nice laboratory for testing radius gap theories there. And finally, TOI 849 is a Neptune-sized, slightly smaller than Neptune-sized planet with over 3 times Neptune's mass, so a very high-density planet in the middle of the Neptune desert, with many theories about how that might have got there, but no clear answer yet, and a growing population of planets near it. The follow-on from this, and one thing I want to say, you can see the sensitivities of HARPS there. So we're finding planets well within the sort of 1 to 4 Earth radius regime. The follow-on from this, and my program going from 2021 on, has been switched name and has a slightly different target. So this is to follow on these deep desert planets that have started cropping up, TOI 849, LTT 9779, TOI 2196 you heard about recently. And to see if we can start doing a more statistical approach to following up planets in near the desert. So the goal here is to take a sample-led approach to find a merit function and make a sample and try and complete it as far as we can, including targets that will be observed by other teams during this, which obviously you can't avoid and wouldn't want to really. We expect to be able to at least cover down to 30 or around 50 systems in this merit function. So hopefully the resulting sample will be nice when it's finished, but it's very much early days at the moment. Current status of that program. You can see here some of the known deep desert planets, and there's 4 here I'm showing that we're currently writing papers up on. There are many more that are either in progress or null results, and I have, as of this morning, updated all of those on the SG24 coordination sheet, so please look there to follow up stuff as it comes up. You can see that we're finding more, this population is growing slowly, and it's a really interesting science case, I think. That is backed up by the Jenkins program, which I'm now going to cover, and thanks to James Jenkins for sending a couple of slides on this, who has a very similar goal to confirm more extreme Neptune-like planets in and near the desert, and have been running for several semesters already. They were the ones who discovered this LTT 9779 planet, and the aim is to precisely measure masses and densities, follow up the benchmark worlds, and generally do a complete program of characterization. Some particular highlights from theirs, which includes the Chiron and Pharos instruments as well, are this LTT 9779 planet, TOI 132, TOI 179, some others. That's the end of my program. I appreciate I've gone through that incredibly fast, so hope the time was about right. Thanks, Dave.
That was terrific. Thank you for representing the other teams. Okay, Guillaume Hebrard, how about SOPHIE and maybe SPIRou?
Yes, can you hear me?
Yes, and we can see you, but you're gone. Now we see your slides.
Okay, so I'm talking about the SOPHIE and SPIRou follow-up. So I'm talking from France and on behalf of the SOPHIE and SPIRou team. So first on SOPHIE is on the 1.3 centimeter telescope observed in optical with different resolution and with an accuracy of about 1 to 2 meters per second. So the radial velocity follow-up of TOI is made mainly through two programs. There is a large program, the transit program that I lead with several COIs, for which we focus on TOIs for the standard radial velocity follow-up. We have about 59 per year for that. We observe 150 TOIs since the beginning of that program. It's mainly for we target mainly giant planets and down to a few sub-Neptune or super-Earth candidates around FGK stars. And we have also radial velocity surveys led by Isabelle Boisse with several COIs, and this survey includes some TOIs. So some results, we published some hot Jupiter led by us or in collaboration with other team. Another example of result is the interesting system WASP 148 with two planets in nearly resonance with TTVs. We see here the resonance, the TTV series in blue, and the one observed by TESS, and the prediction that José Almenara made with the photodynamical analysis, probable mutual inclination between both planets in this system. Other result with super Neptune detected, that system where Luisa Serrano talked about that a few minutes ago. A system published by Neda Edari, so that one was in a radial velocity survey from SOPHIE, but after it was published as a TOI, so we detected with SOPHIE in collaboration with people from USA, with IRS and APF. So it is a dense sub-Neptune. And now with SPIRou, SPIRou is working on 3.6 meter at Hawaii, the CFHT. It observes in the infrared range with that resolution and typical radial velocity accuracy. So with SPIRou, we do the follow-up of TOIs mainly through a large program. It was the SPIRou Legacy Survey, and then there is the SPICE program. The SPIRou Legacy Survey is over, and we just start the new one, the SPICE program. Jean-François Donati is the PI of that program. Myself and René Douaillon are the leader for the TOI follow-up with some collaborators. So we have about 39 per year for the TOIs with SPIRou. We observe 20 of them since the beginning of that program. And there are also smaller PI programs observing a few TOIs. So some results, we published a transiting brown dwarf, also a transiting sub-Neptune. And if I focus on one of those results, by Charles Cadieux and collaborators, released a few weeks ago on that super Earth in a temperate orbit transiting an M dwarf. We see the radial velocity curve obtained with SPIRou, and that object is very favorable for atmospheric characterization with JWST. And latest result that I present to you today, obtained with SPIRou and the young system AOMIC, which hosts two transiting planets. So first with SPIRou, we measure the ubiquity in that system, and also it was led by Eder Martioli and led by Baptiste Klein. We published a radial velocity detection of that star. It was not easy because it is a particularly active star. We see the radial velocity here. The radial velocity due to the planet after correction of all the stellar effects. And here we can study the stellar effects, the stellar activity, also thanks to the fact that SPIRou is a spectropolarimeter, so we have polarimetry. And so we continue those programs, both with SOPHIE and SPIRou. Thank you for your attention.
Thank you for staying on time. And that's great. Next, Lars Bouchy will talk about THEISS on the Nordic Optical Telescope. Go ahead, we see your slides.
Great. So yeah, I'm going to talk about the THEISS spectrograph at the Nordic Optical Telescope. And so it's really a nice spectrograph and telescope. So I put this rather romantic slow motion movie as an advertisement to visit, because if you want to steer a telescope yourself, this is a great opportunity where you get to sit alone at the telescope and observe. So find a partner from one of the Scandinavian countries or go through the Opticon angle to get the time on the telescope. So the THEISS spectrograph is a 67,000 resolution optical wavelength going slightly into the redder part, as you can see here on the slide. PHEIS was not built for precise radial velocities. In fact, it was up at the telescope and later moved down to its own building. It's temperature controlled, but certainly not at the millikelvin level, and it is not in vacuum. And so we undertook some hardware changes to try to optimize the radial velocity precision of the spectrograph. And we installed a new octagonal fiber feed that really worked well, so that it removed all the scrambling issues. We installed a pressure chamber to account for the atmospheric pressure changes, and an etalon to try to calibrate the spectrograph, which did not work as well as we'd hoped. So we didn't quite meet or get down to the few meter per second level with PHEIS. It's more at the 5, 6, 7, 8 meter per second level, depending on circumstances at the moment. But nevertheless, we had a 90-night program composed of a national Danish program and a TESS-funded program of 45 plus 45 nights in around 2019 to 2021. And so we made a number of reconnaissance spectra with PHEIS and attempted radial velocity mass measurements of some of the targets. And so here's an overview of the papers we contributed to using this program. So here's a number of TOIs where we contributed to the radial velocities, and many of them are actually published now, I think. And it says unpublished here, but they're published, all of them, I think. And the other contribution we made is stellar parameters for all the TOIs we observed. We observed almost 200 TOIs, about 1,000 exposures nearly. And they've been analyzed with the stellar parameter classification tool called SPC, and all these parameters that we found are uploaded to the exoplanets website. So you can go there if you want to find some of the PHEIS spectra. And then to the right, here's a figure from one of my PhD students' thesis showing the velocity, showing the temperatures, gravities, and metallicities of the TOIs that we looked at with PHEIS. Additionally, we managed to actually observe an atmosphere of 2 planets, Kelt 9b and Mascara 2b, or TOI 1150 and 1151. Which was published by one of my PhD students. So as far as we know, this is the smallest telescope aperture size to actually detect the atmosphere of an exoplanet. So that was published by Beloruff in 2000, or this year, in fact. And then we contributed to Andrew Vandenberg's orbiting white dwarf planet candidate. And there are numerous other teams that have used PHEIS, for example, KESPRINT, as we heard earlier, and others that were a bit too numerous to name here. So I will just say that there's many people that use PHEIS and advertise that you should go use the telescope if you want. That's all. Thanks.
Thank you, Lars. Okay, I think we almost finished with Europe, but let's move to the US with NUID. Cullen Brake has agreed to make this presentation for the NUID team. We see your slides. Yes, go ahead, Cullen. But we don't hear you.
You did? Sorry about that. Thank you, Dave. I'm pleased to have this opportunity to tell you about NUID, pronounced like fluid, and some of the exciting early test science that we've been doing and the community has been doing. Start with just a brief overview of NUID. NUID was commissioned in fall 2020, has the dubious distinction of being commissioned twice because the first commissioning effort began right before COVID shut down. And it's at the Wind Telescope at Kitt Peak, a 3.5 meter telescope. There are about 100 nights per year available to the community through NOIR Lab. From the instrumentation point of view, what makes NUID maybe different or special is that it has a very wide wavelength range from calcium H and K all the way out into the sort of Z band. And it's designed with high throughput in the red and the blue. We have a laser frequency comb, 2 observing modes for high and low efficiency or high and low resolution, and it's highly stabilized from the point of view of temperature. It's all operated through a queue, and those observations are executed by on-site observing specialists. And there's an automated data pipeline, and you can just get RVs in the mail if you like. And of course, there's access to other data products. And this is all part of the NASA NSF NN Explore program. I wanted to show sort of one obligatory plot of everyone's maybe favorite quasi-standard star, Tau Ceti, where we see about a meter a second or a little better over the course of a year. And we're fairly confident that this is substantially above the intrinsic instrumental limit. I wanted to highlight 3 specific areas where NUID is already being used for TESS science. The first is Rossiter-McLaughlin measurements. Because NUID is Q scheduled and it's very efficient, it's a very good facility for these types of measurements. I wanted to show just 4 already published examples of WASP 148, GJ 3407, as well as 2 TOIs, 1268 and 1478. So we look forward to seeing a lot more exciting roster effect science coming out of NUID. There's also been a focus both on our team and in the community of long period planets. So these are 2 examples of TOIs where the orbital period is months, a couple of months approximately. On the left, we have confirmation of one of these planets by actually measuring the Rossiter effect. Again, NUID is quite good for that because of the Q scheduling. And I look forward to seeing a very nice talk this afternoon by Jiayin Dong, who will talk about this particular TOI here, 1859. And on the right, this is a very long period, very eccentric system that Arvind Gupta is following up. And again, the Q scheduling allows us to cover the phase here pretty well. And a third area to highlight is M dwarfs. So because of the intrinsic high red sensitivity, NUID is very good for observing M dwarf TOIs. These are 3 examples here. And if you squint, you might say, well, those error bars look more like a few meters a second, not the advertised sub-meter a second. But I want to highlight that in the optical, many of these objects are quite faint. For example, Caleb Kanyas, who may be on the call here, has a nice recent paper about an M dwarf TOI that has a D magnitude of about 15. So in summary, NUID was fully operational and doing great science before the recent Contreras fire, which happened at and near Kitt Peak this summer. I'm happy to report that things are well back on the way to normal operations at Kitt Peak. NUID is a great facility for TESS follow-up, particularly for faint or red objects, and the Q scheduling really enables high impact observations of TOIs. And I want to emphasize that NUID is available to you, the community, through Noir Lab, and also through collaboration with WIN partner institutions. Thanks very much.
Thank you, Colin. Fantastic. And next we have Howard Isaacson talking about the California collaboration, CPS, using a couple of instruments, high-res on Keck and APF.
Good morning, Dave. Can you hear me?
Yep, we can hear you, and we see your slides.
Excellent. Well, thanks for having me today. It's a pleasure to represent the team, some of which, or all of which I should say, you can see here. I'll just note it's also incredible to see each RV team with about the same size as the entire Kepler follow-up team about 10 years ago. So it's amazing where the field has come. It's a pleasure to see everyone's work today. So we have a large consortium here, a large group of institutions, professors, graduate students, and researchers doing work on the Keck high-res instrument and the automated planet finder. We've come together for trying to conquer a whole different slew of science cases, a few of which I'll try to enumerate today. All right, so first and foremost, we tried to put this survey together from the bottom up. One of the few criticisms of Kepler was that it was difficult to reproduce the sample and the target selection. So from the beginning, we've attempted to document a reproducible method for producing this sample that includes a lot of main sequence stars, as well as a few evolved systems, many according to the different science cases that the different PIs have been interested in. This is summarized in Ashley Chantos's recent paper that enumerates the science goals that include, of course, measuring small planet masses, but also discussing system architectures and dynamics, thinking about stellar evolution and how planetary systems develop. There's a program to study stellar activity and Doppler noise, which is, I guess, in some sense, part of every radial velocity survey, as well as some stellar obliquity measurements. And the next few slides, I'll just try to highlight a few of the works so far that some of our colleagues have been working on here. All right, so one of the first early TESS Keck survey papers was led by Lauren Weiss on TOI 561. This is an galactic old star identified through the alpha element abundance and through the galactic velocities. We're able to measure all three of the small planet masses, and you can see those plotted on the planet size, planet density plot on the right here. Some of the roster and buffer measurements, which we've heard a lot about, are posted here. WASP 107b and TOI 1726. This paper is led by Ryan Rubensall, and you can look forward to a new paper coming out that highlights many of the USPs that have been found so far, as was shown in one of the earlier talks this morning. You can see that they commonly lie along these Earth-like and rocky contours, and so stay tuned for more on that. Some of the other science that you can do with radio velocity surveys is measure the masses that can contribute to target selection and understanding of planets that will measure with JWST. So Nick Scarsdale at Santa Cruz, and then soon to come Joy Murphy's work is focusing on measuring masses for some small planets that have high TSM metrics. They're going to be good candidates for measuring planetary atmospheres with JWST. In addition to measuring planetary atmospheres and masses that way, we can also use the TESS data itself to look for interesting candidates. So Mason McDougall at UCLA has been working on a pipeline that identifies potentially eccentric planets and then following them up with radial velocities to determine the exact eccentricities. Of course, interested in planetary dynamics, and system architectures. Of course, the long-term surveys have been really good, as has been mentioned by Enric and others, that you can start to find non-transiting planet systems. So this system led by Jack Lubin, UC Irvine, HD 1939, has 3 transiting planets, as well as a long-term non-transiting planet and a long-term trend that's been identified so far, and observations with that are ongoing. I'll note the APF observations here were a nice complement to the high-res observations because it has a very long, very common cadence, right? Near nightly observations with the APF, which was able to fill in some parameter space for the non-transiting planet. Emma Turtleboom at UC Berkeley has been able to combine some high-res data and some HARPS North data to produce this nice RB time series for TOI 1246. And then here, as was thought it was mentioned earlier, Judah Van Zant at UCLA is working on following up a lot of the TESS systems, both those that we've worked on in TKS and some previously published planets, to look for long period companions. And here's a couple of them here. These can be used for dynamics as well as occurrence rates. And finally, I'll just leave up all of our planet masses and radii, most of which are soon to come, over 100 in total. And yeah, thank you for your attention. It's a pleasure working with this group. Nice to see everyone again.
Thank you, Howard. Okay, let's move on. Johanna Teske is going to talk about the Planet Finder spectrograph. She has a very large program there, but there are several teams using that instrument. I see your slides.
Excellent. Can you hear me?
Yes, I can hear you. There you go.
All right, great. Thanks, Dave. Okay, so yes, I'm talking today about the Planet Finder spectrograph, which is on Magellan 2 telescope here, showing this beautiful photo from Uri. And just as a quick reminder, PFS is an iodine cell spectrograph. It's mounted, like I said, on Magellan, which is a 6.5 meter telescope in the southern hemisphere. So we're mostly, operating in the optical, resolving power around 130,000. And since TESS, we've been getting something like 30 to 50 nights per semester across the entire consortium. So not just for TESS follow-up, but that's been a big increase in our allocation. And I'm showing the core team members, mostly from Carnegie. And then I think I got all of our collaborators, but I apologize if I missed anyone. So I think the idea here is to report mostly on level 1 science efforts. So I have a kind of before and after plot. So in late 2018, PFS had not been doing a lot of transiting planet follow-up, some HATS and K2, but we didn't have access to the Kepler field, of course. And so we are spending most of our time on searching for new RV planets. And that's what the small planet mass radius diagram looked like at that time. And then October of this year, we have this explosion of small planet measured masses and radii, a lot from TESS. And in this plot, all the points with X's are cases where PFS has contributed or led those publications. And so I wanted to highlight a couple of those cases. So I have two from Jen Burt. So she led two papers on some interesting sub-Neptune planets. One is this cooler temperate one, TOI 1231b, which is good for comparative exoplanetology, as shown in that bottom left plot. And then also searching for Lyman alpha in the exosphere because of the star's high systemic velocity. And then on the other side of things, a hot sub-Neptune, TOI 824. And so the idea there is maybe that would actually be better for testing the other end of the equilibrium water feature trend. And that's also a possible candidate for helium observations. It's around the K dwarf. And I'll also highlight Zara Essek has a talk later about a massive USP planet. And then Sam Quinn has been doing small planet follow-up, and we have other previous papers led by PFS team members in this regime as well. But we're also contributing to some of these larger efforts, some of which you've heard about already. So there was one of the first TESS papers, TOI 562, and this was an interesting transiting Earth-sized planet, but then with these other RV-detected planets. This, of course, follows into the sample that Raphael and Enric just published, showing these three different density regimes of planets around M-dwarf systems, which I'm just a result that I'm super jazzed about. So if you haven't read that paper, I highly recommend. There was a KESPRINT paper that we contributed to, TOI 560, and this was an interesting system. It's very young. It has these two sub-Neptune transiting planets that might be experiencing, actually, I think one has a helium one detection already, so important for probing the process of atmospheric loss, which we think, of course, is common in these short period planets. And then what I like to think of as Jen Winter's system, TOI 455, which is this hierarchical M-dwarf triple system with two planets detected around the A component. And this was a really monumental effort combining in data from lots of different instruments. As Dave mentioned, I'm leading the Magellan TESS survey, which is surveying 30 small test planets to focus on sort of a population level analysis of these planets, trying to understand their different formation pathways. And there's lots more about it in my 2021 paper. But I also wanted to mention Tansu Dalen is focusing on one of those systems. I think it's a 5 or 6 planet system, TOI 1233. And then this is leading, like many of these planets, into JDOS-T synergy. We have a large GEO program accepted that will start getting data next year, which is a subset of these MTS targets, the GAT transmission spectroscopy. And I was also really excited to see that many of them are in this potential water world population as well. And then finally, I just wanted to highlight a few other non-small planet, but also I think really interesting science cases. The giant planets around dwarfs. I am not a huge fan of giant planets, or I have been in the past, but this work is making me a fan of giant planets. And Shubham Kanodia is a new postdoc at Carnegie, also working on this. We have several people following up single transiting planets and really trying to get at the longer period systems that are, of course, are more challenging to detect with TESS. And then a group of folks doing RM and Doppler topography observations to really study the dynamical histories of giant planets. And Sam, he has a talk later today about his Grand Unified Jupiter survey. So PFS is contributing something like 30% of small TESS planet mass measurements. Not always leading the papers, of course, but contributing data. And then we have those other compelling science cases as well. So that's it for me.
Thank you for that great summary of the work going on at PFS. Okay, now we're going to move to Hawaii, I guess. Maroon X. And Madison Brady is going to give this presentation. I see your slides. Do I hear you?
Hi.
Yes, I hear you.
Right.
Yes.
So, hi, everybody. My name is Madison Brady. I'm a third-year graduate student at the University of Chicago, and today I'm just going to provide a quick update on Maroon X. So, just to start, Maroon X is a high-precision radial velocity spectrograph installed at Gemini North. It has visible and near-infrared wavelength coverage. It's been able to achieve a sub-meter per second radial velocity precision on a lot of targets. Overall, it's been in regular use since about May 2020, and operations are currently ongoing, and it is available to the public for proposals through Gemini. And it's been receiving a lot of time on Sky, both this semester and last semester. It's got around 280 hours of like dedicated time, just in band 1 and 2, which is like generally good conditions. And like looking forward, we're expecting a laser frequency comb installation in February 2023, which should even further improve our sort of baseline calibrations. One of the projects that I've been involved with in the last couple of years is specifically a survey of TESS planets around nearby M dwarfs. So we're attempting to perform pretty extensive follow-up of all of the validated TOIs within about 30 parsecs that are visible from Mauna Kea, with the intention of achieving a 10% or less mass error measurement on all of these planets. Overall, our sample currently contains about 30 transiting planets with stellar V magnitudes of equal to about 17 or less, and the sample is continuously growing as TESS continues to discover new planets. This plot here is a histogram of the percent mass error of all of the planets with measured masses in our sample. Overall, you can see that there's a pretty substantial number of planets that already have mass error below about 10%, though of course we still have a large population of planets that either haven't been observed enough or have enough additional planets in the system that it's difficult to characterize the exact mass, and so we're continuing to follow up on those systems. One of the interesting science questions that we can answer with this sample and that a lot of other groups have been talking about today is the result from the CARMENES paper earlier this year. This is a mass radius plot of a bunch of M dwarf planets with well-characterized masses and radii. And you can basically see that a large proportion of these planets fall either on a sort of Earth-like composition line or a line consistent with having a roughly 50% water composition, with the idea being that perhaps the radius gap around M dwarfs is explained by a sort of composition difference in the cores of these planets. Now we can kind of look at our specific sample, which is kind of constrained and a little bit more understood in terms of like the TESS statistics and is volume limited, to sort of see if we can sort of follow up those results. This is the currently like sort of well-characterized mass radius sample planets in our sample currently. And you can see that most of these planets seem to have compositions consistent with being mostly rocky or having Earth-like compositions. There are a couple that are consistent with having some sort of substantial hydrogen envelope. And then you can see there's a population of some planets that seem to scatter around this sort of 50% water line, but they don't necessarily fall exactly on it. However, most of these planets have relatively low mass precisions. So one of the things we're interested in trying to do is to either continue following up on these planets to improve the mass measurements, or to look at some of these planets for the first time to really improve those mass errors. Just to kind of move on and discuss some of the other most recent publications using MaroonX data. Well, we have contributed a lot of data to various papers characterizing various TESS planets, frequently in combination with other instruments like CARMENES. This plot on the left is from a paper that used CARMENES and MaroonX data to achieve a less than 5% mass error measurement of Lisa 486b. And this plot on the right also uses both MaroonX and CARMENES data to study the system TY 1468, which is also in that 30 parsec sample, where you can see that the system is consistent with having one star that's sort of a bare rocky core, and another one that's consistent with either having a substantial gaseous envelope or some sort of substantial volatile content. So this is very interesting for actually considering those radius gap questions. This was just brought up earlier, but also we have contributed data to the LTT 1445A paper, which is the nearest transiting M dwarf system with 2 super Earths. And then also quite recently, MaroonX data was contributed to the paper to characterize the TOI 620 system, which is a potentially extremely low density sub-Neptune. I think I'll stop here so that you have time to move on to the next person, but thank you everybody.
Well, thank you for that. And I have to comment that I'm impressed that the Maroon team is so willing to contribute to other papers that needed to have that little thrust to get them over the finish line with a set of really precise velocities. That's a remarkable philosophy and attitude towards cooperation.
Thank you.
And now we have also from Hawaii, Peter Plafchan talking about ice shell.
All right, can you hear me?
Yes, and we can see the slides.
Great. Okay, so here to talk about ice shell, the test follow-up that we've done. And first of all, I have to thank the team, particularly Bryson Kale, who's now a postdoc at the NASA Exoplanet Science Institute, graduate students Mohammed El Mufti and Justin Wittrock, who are both testing the job market waters this year, And Michael Reif, you just heard about his paper on TOI 620, which had contributions from Marunex. Thank you. He's a new graduate student at MIT, so in your neighborhood. To date, we've had 14 published papers using iShell data, mostly where we've contributed our data to other teams, but and collaborating with others in TFOP, representing around 20 planets. And here's the comprehensive list. In the upper right, just want to highlight TOI 442, which involved PFS, CARMENES, ESPRESSO, HiRes, and iShell. This is actually one of our better detections that we had with just the iShell data. And that was a really neat M-dwarf Neptune in the Neptune desert. We also had TOI 732, contributed TOI 732 BC, which was 2 planets orbiting the M3 dwarf, with planets astride the Radius Valley. And of course, as many of you know, the discovery of the AU mix system, with many teams contributing to that data set. And interestingly enough, those mass measurements for such a young system are showing densities that are not all that different from mature Neptune planets. And that poses a really interesting question, because we've seen something similar with 2 of the planets in the V1298 Tau system, another 20 mega-year-old system. So how are these planets so dense already and not super puffs like the Kepler 51 system? More recently, we led a paper also in parallel to the Berrigan paper on TOI 560, which is roughly a giga-year-old K-dwarf system with 2 planets. And fun fact, it's a great target for JWST. Turns out when we're looking at iShell at K-band all the way out 2 microns, well, that's also important for brightness at near-infrared wavelengths, is also important for atmospheric characterization. So we tended to select a lot of targets for our program that overlapped with good targets for atmospheric characterization. But TOI 560 in particular, the planets are nearly equal in size. And from a Spitzer observation, we've been able to show that the inner planet is mildly eccentric, which is a bit unusual. In addition to that, there's roughly once a year, there'll be double transits visible for JWST. So if anyone here is interested in atmospheric characterization, I'm not going to do this. But if anyone would like to propose to observe the system, you get roughly once a year visible shot of getting 2 transits to be able to do differential atmospheric characterization in this interesting system. Now, we already mentioned TOI 620 in the previous talk, as well as some of these others that we heard from Amy earlier today about TOI 461. We have a nice iShell RV follow-up on that system that'll be coming after her paper, as well as a bunch of indirectly related papers that have come out of group kind of as a result of the work that we've been doing with iShell TFOP, including mitigating the impact of telluric absorption, and starting to look at spectral line depth variability, and also SG1 work, as shown here. Michael Reif also published a paper in my group on automating our campus point 8-meter telescope for SG1 observations for TESS. And AUMIC is a GIF system that keeps on GIFing. It has very strong TTVs, and there's a few papers out on that as well. So what's iShell's niche? The original target selection was near IR bright, which was also good for JWST characterization. It turns out most SG4 teams were also interested in bright, cool stars, even with 10-meter apertures. So we had to collaborate a lot, and I think I am very grateful that we were able to share RVs with all of these teams and achieve greater science results than we would have done working independently. But we did end up having significant overlap in our target selection with other teams. And to date, we've mostly exhausted our TOI list of targets that are down to about 8th magnitude at K. And so we kind of hit the point of diminishing returns. And the newer TOIs coming from the FFIs tend to be exclusively fuller. We're also challenged by other SG4 teams having far more observing time. And it was also harder to reach the same RV precision in terms of photon noise RV precision at K-band compared to visible wavelengths, which kind of canceled out our stellar activity advantage working out in the K-band. One thing I want to say about TOI 560 and AUMIC is in all the cases that we've worked on, we've developed a chromatic radial velocity analysis, and a lot of people don't kind of know what to do with this near infrared RV data, but we very clearly have detected wavelength dependence of stellar activity in the radial velocities for K dwarfs and M dwarfs of ages up to a gigayear. So we're kind of winding down our program at this point in time, and there's a lot that's changed since we started with iShell back in 2018 for TFOP, and there's a lot more instruments now online at higher precision than there were just 4 years ago, as listed here at the bottom. So we still have a few TOIs to publish, and I think at K-band, iShell's niche remains uniquely poised, in the US anyway, to tackle M-dwarf stellar activity when done in conjunction with visible RVs, but that could be hard to schedule, multi-telescope coordination. So I'm hoping NERPS and some of the other facilities here can do a good job of that. But I think we have a very powerful technique in distinguishing stellar activity between from planet signals by doing this very long wavelength lever arm. We also haven't explored any of the line-by-line variability, such as Zeeman broadening or flux variability in individual lines. With that, I'll stop.
Can you finish up, Peter?
All done.
Good. All right, we have an in-person presentation from yours truly. I'm going to talk about the HARPS North collaboration, which was a project that Michel Mayor and I cooked up in 2005, 4 years before the launch of Kepler, because we knew we needed more PRV facilities in the north. It's a large collaboration, an international collaboration, because we ended up having to add new partners and find new funding after we lost a lot of our funding due to the Great Recession in 2008. Anyway, we started science operations in 2012. We have published masses of transiting planets by the collaboration itself with guaranteed time. A lot of this dates back, transiting planets before TESS, 26 masses for Kepler, 13 for K2, 7 so far, and 16 other sources of transiting planets. And there's a similar number from the community. We get 80 nights a year with GTO time, and altogether about half of the time on the TNG, the Telescopio Nazionale Galileo, is dedicated to observations with HARPS North. And I counted up last night, there are currently 15 TOIs that we're observing or have papers in preparation. So there's going to be more than a dozen additional masses from HARPS North over the next year, I would guess. Many of these have more than 100, 10 of these have more than 100 observations. That's what it takes when you're targeting the limiting cases. Anyway, I wanted to say something about the publication record from SG4 at the end. I've been watching all these presentations, and I'm just overwhelmed by the number of teams and the number of people and the number of facilities that have agreed to work together and efficiently follow up the small planets from the TOIs from TESS. And an indication of how well this has worked is some numbers I got from Sam Quinn, that out of the 100 or so masses in 68 systems, 60% of them are by single teams, collaborations for 35% of them, and only 6% where there were independent submissions from 2 different teams. In one case, actually 3 different teams. And those were coordinated, they were simultaneous submissions. So I think it shows you how well SG4 has worked. And I want to thank everyone for buying into our philosophy. And now we have a bonus track because David Sciardi, you came in on the red eye, didn't you?
Yeah. 5 hours of late flight.
Okay, he's going to talk about another very successful subgroup, subgroup 3 for high spatial resolution work, finding companions lurking in the shadow of TOIs.
Hello, everybody. I'm David Charity. I'm at Nexi, and I'm the leader of the SG3 group. And I specifically want to thank Dave Latham for accommodating my travel schedule so I can get back to Europe, so I could actually give this presentation in person, so I can see the group of you. This is a pretty short overview of the program as a whole. I am happy to talk about it in more detail and some of the actual science that's coming out of this program, not just the support of the TFOP as a whole, but this is basically a summary of the content of what we've been doing, and I'm happy to answer more. And I'm also keenly aware I'm sitting between you and lunch. SG3, just as a reminder, the intent here is better than seeing limited imaging, where we are trying to identify stars that are photometrically blended with the primary target, and we want to identify both bound and unbound stellar companions. In particular, this helps us inform the statistical validation for the presence of the planet and get rid of the eclipsing binaries and the hierarchical triples if best we can. But also, much more importantly, is it helps us yield accurate transit depths and therefore planet radii. Just as a reminder, the graph on the bottom, that if there's a blended star, bound or unbound, that star will fill in the transit and you end up with the wrong transit depth and therefore the wrong radii. And the density that you get for the planet goes as the cube of the radius, right? So this is not, it's not a trivial effect. So that's one of the primary reasons for doing this kind of work, not just the get rid of the false positives. So the organization, it's a little bit smaller than most of the other groups. There's about 70 working members from around the world. It is primarily optical speckle observations and near-infrared adaptive optics observations. So a slightly different slide. This is the wrong version, Abby. It didn't update. It's weird. Anyway, but we also use Gaia. It's fine. It doesn't matter. We also use Gaia, and there's also a lucky imaging group. But it's a combination of different techniques, sensitivities, and filters, because every telescope and every has its own resolution based on the wavelength and the diameter of the telescope, and also the outer edge of the field of view also plays an effect, how far out you can go. But there's a really nice overlap between this group and what Gaia is providing at about the half arc second to arc second level, and that is a nice synergy. This particular collaboration isn't quite as formal as the other subgroups in the sense of we're not trying to specifically prevent observations of the same target by different groups. And in fact, we want multiple observations from different groups because of the different wavelengths and the different resolutions. We do try to organize so that somebody on KEK doesn't observe the same target twice on KEK, but having an additional observation from KEK and the VLT is actually quite useful. The data products, in addition to the imaging summary, there's the images and the previews that go with it and the contrast curve, all necessary for the papers. And most groups are now producing publication quality images that are getting uploaded to the FOP that the users are just downloading and including in their papers. And now we're starting to be much better about including our detected stellar companions. I want to point out that the priorities on the SG3 are slightly different than the priorities for the other groups. We don't use these as high priority, low priority, but rather we use these as flags to indicate what has been done or not been done. And so you can read the numbers there, but effectively what we do is, no observations have been done. It has AO, it has speckle, it has both. It's a false positive, that kind of idea. So those codes are there to help with the planning and also for you guys who are not part of the group to understand what's been done or not been done. But I encourage you that even if something is listed, to at least contact me to get an assessment, or the owners of the data to get an assessment of what's been done in that data, because every group has slightly different sensitivities, resolutions, etc. So here's a summary of what actually has been done. And 67% of all the TOIs have some form of high resolution imaging. I actually was quite stunned by this number. I didn't realize it was quite this high. And if you look at systems with small planets, so systems that have planets of for Earth radii or smaller, that fraction is something like 85%. The group has done a really remarkable job to do this. And it's because we have these large dedicated programs, and 2/3 of the observations actually are optical speckle, either from SOAR or Gemini North and Gemini South. And in fact, the Gemini North-South programs actually make up about 50% of all the observations. These two very large, long-running programs on the 8-meter telescopes have been extraordinarily useful. But again, for any given TOI, I really encourage you to assess what really has been done to determine if it was sufficient. And if it hasn't been sufficient, to let us know, and we can make sure that your object gets observed in the right way. So this is just a summary of about the 1,400 TOIs that remain unobserved. It's just a plot of orbital period versus radius. I just wanted to, to show that it's sort of all over the map, but at the phase space for TESS, but at the bottom where the smaller planets are, we're actually starting to clean those out. And I think that's really great. And then finally, or not finally, but on the next slide, our companions are starting to be listed more consistently on the ExoFlop. And there are currently over 1,200 entries in that table just for stellar companions. And each row in that table is one detection per observation, per filter, per telescope, per whatever. And I wanted to show this figure on the left here, that this was some work that was done by Carl Ziegler, where he was showing how Gaia can contribute. And that line that he drew is sort of the guesstimate of the sensitivity of what Gaia's capable of detecting. And you can see that it does fairly well down to about half an arc second, and then really well out past an arc second. That same line I sort of drew on the figure on the right. And you can see that a significant fraction of the stellar companions that we are finding are well inside the limit of Gaia. And so the combination of Gaia and the high resolution imaging is super powerful in helping us determine the presence of a stellar companion. And if that object happens to also be detected by Gaia, then we have a real opportunity to get distance and proper motion as well. And then my last slide before Dave tells me to stop talking is here. I'm not going to read this. I do want to make one mention. Something happened last week in our community that a lot of people aren't aware of, and I only found out yesterday, and I wanted to share this with you. So many of you know Margaret Mexner. She is now the director of SOPHIE. Her brother, who is a professor at the University of Arizona, was killed in a shooting accident by a graduate student, and his funeral is today. And many of you know Margaret and Margaret well. She was at Space Telescope forever, and I just if you feel like you know her well enough to reach out to send her best, I think that she would really appreciate that from our community. Academics communities are all very closely tied together, even though her brother was not in our field. And I didn't even realize this until somebody had pointed this out to me. And so I just wanted to make a mention of that. I'm not trying to make a downer of our lunch and this wonderful meeting of all of us being together, but I thought I would share that with you if any of you know Margaret well enough to send her your best. On a slightly happier note, I just wanted to thank the whole group of you. The TFOP has been a lot of fun, and the SG3 coordination has been enormously fruitful, and there's an enormous amount of science coming out of this group as well, not just the support of the TOIs. Anyway, thank you, and thank you.
We can take a question or two. Anything in the audience? Anything online? Nothing? People want their lunch. Well, they have a little more than an hour for lunch. Be back here at 1:30. No, that'll delay the whole afternoon. You can eat lunch in 70 minutes, can't you?
So also be available so you know where lunch is, but if not, there is a map printed out from this, and it's also on the wiki page. I put in all of my. I said I put in a big